A small fan can be a perfect-looking copy of a large one and still miss the predicted curve. Geometry may scale, but the balance between inertia and viscosity can change, and that balance is Reynolds number. Reynolds number is dimensionless. Re equals density times velocity times characteristic length, divided by dynamic viscosity. The same relation can be written as velocity times length divided by kinematic viscosity. The phrase characteristic matters. For a rotating fan, engineers may define velocity from rotational speed in diameter, and length from diameter or blade chord. Use one declared convention consistently. There is no single Reynolds number for every location in a fan. Geometric similarity means corresponding angles, profiles and length ratios are preserved. If every length grows by a scale factor K, clearance, blade thickness, roughness and inlet geometry must also be checked as ratios, not just the outer diameter. The familiar fan laws are a similarity reference. At corresponding flow coefficient, flow scales with speed times diameter cubed, pressure with density times speed squared times diameter squared, and power with density times speed cubed times diameter to the fifth. Those exponents do not guarantee identical efficiency. With a diameter and tip speed Reynolds convention in the same fluid, Reynolds number is proportional to rotational speed times diameter squared. At equal RPM, a fan twice the diameter has roughly 4 times that Reynolds number. At lower Reynolds number, viscous effects are relatively stronger. Boundary layers occupy a larger share of a small blade passage, transition and separation can shift, and leakage or surface texture can become more important. There is no universal critical value for all fans. Matching Reynolds number is not simply choosing the same RPM. A scale model may require a different speed, fluid viscosity, density, or pressurized test medium, then Mach number, structural limits, motor capability, and the intended flow coefficient must still remain acceptable. Real product families show why physical evidence matters. Different crossflow diameters are built and measured as separate models. That footage demonstrates hardware in test context, not proof that Reynolds number alone caused any performance difference. Separate size families also carry separate PQ curves and data tables. Compare them only after normalizing flow, pressure, and power into agreed coefficients and confirming geometry, speed, density and test installation, not by stretching one curve on a slide. Other scale breakers include relative roughness, tip clearance ratio, blade and edge thickness, leakage paths, compressibility, motor and bearing losses, manufacturing tolerance, guards, inlets, ducts, and instrumentation uncertainty. For a scale-up, document the geometry ratios, characteristic redefinition, flow and pressure coefficients, Mach number, fluid properties, speed, roughness and clearances, test setup and uncertainty. Then validate at more than one size before releasing the production prediction.